Hey, how are you doing? I hope you're doing well, and I hope you're enjoying all the things you're learning and experiencing in the world of IT. I am very fortunate to have a great group of colleagues. My name is Darlin. I am chairman of three groups, the London Central, North, and South branches of the BCS. And the great colleagues I've got are my committee members. We are running lots of initiatives, including, for example, one on cloud, one on AI, and also one on cyber. And that is the focus of tonight's session. We have got an event on cyber, but it used to be you could just talk cyber. Not anymore, as you know. What kind of cyber? What aspect are we talking about? Are we talking about ransomware? Are we talking about software? Are we talking about hardware? Well, in this evening, we have got a very unusual session on critical network infrastructure attacks. So indeed, a great aspect of cyber to consider, one that we don't think about often enough. Please sit back, enjoy, and let's watch this session on cyber critical network infrastructure attacks.
Hello, good evening. Can you all see my slides?
Yes, we can see.
So my name's Simon Clayton-Mitchell. I was working as an independent cybersecurity consultant, which was my role within Digital Works Group. We're a group of independent digital consultants. I have just recently joined an IT technology company called Node4. I've got my details there. If anybody's interested in reaching out, my LinkedIn profile is there. I think David said he put this in. I'd like to extend a thank you very much to Dallam, David, and the rest of the BCS team for allowing me to come and talk to you. I wanted to talk to you about BGP hijacking. So let me just, okay. Fine. So I'm going to be telling you at the beginning what a lot of you already know, which is how the internet is different from previous networks. But I think just to put BGP in context, it's important just to revisit that. Before the internet, which for me is, for many of us, is really quite recent. It was switch network with dedicated paths. So if you wanted to communicate between Chicago and London, your traffic flowed through a series of predefined POPs, points of presence, and each time you sent data, it followed exactly the same path. So it was a nailed up path, and that was it. If something happened to that path, if there was an interruption and you tried to send more data, it couldn't arrive. It wouldn't be transmitted. There was a break in the network. You had a problem, and it was trying to address that problem. It was originally the US military actually that got involved in that, decided they needed a network protocol to deal with that, and of course that gave us the internet that we know today. So dynamic routing, again, we want to send information between Chicago and London, and this is an oversimplification, but each packet or set of packets can follow a completely different path to get to the two locations.
Your screen's not showing. Are you supposed to be showing it still?
Yeah, so you're not seeing my screen?
No, it's just you full screen now, your webcam.
Okay, we'll go back to this. I don't know what happened there. So we'll just go back. So this is the switch network dedicated paths. Data follows a standard route. If the paths break, you can't send any more data because the dedicated path is taken down. As I said, the American Defense Department wanted to address that, came up with dynamic routing, and each packet or set of packets could follow a completely different path through the network to get to the location. And if there was a break, they simply routed around it. Now, BGP is, the question is, how do you do that? So how does the internet know how to find people? Can you hear me okay?
Yeah, we can hear and see.
Yep. So roughly speaking, DNS, domain name server, is the internet's address book, and I'll just go through that very quickly in a second. But if DNS is the address book, then BGP, or Border Gateway Protocol, is the internet roadmap. So we're all familiar. I think most people will be familiar. You type in something like Amazon.com, Starbucks.com, and the DNS server turns that into an IP address, a physical location on a server somewhere in the internet that you can then reach. Border Gateway Protocol was how to get to the address. So in the early days of the internet, what they decided was that every network had a unique number, its autonomous system number, or AS number, sometimes just called ASN. So for example, AT&T's AS number is 20057. Border Gateway Protocol uses AS numbers to show the route to IP addresses. And BGP, external BGP, shows inter-network routing. So what it does, it defines the network, the routing between networks. It doesn't care about how you route within a network. Within the network, that's up to the network provider. And this simplified routing within the network considerably. So as I say, it doesn't say anything about how traffic is routed intra-network, and we'll actually come to that later because that also represents some issues for critical infrastructure. In 2020, the BGP routing table was about half a gigabyte, 500, just over 512 megabytes of data. And that's continually being updated and shared between providers. So how does BGP actually work? So can everybody see that simple network that I have drawn? David, are we all good with that? Yeah. So I've deliberately used very simple AS numbers. So there is a network called 11, network number 11, and it happens to hold YouTube on its servers. So network 11 owns YouTube. So there we could imagine that's in California. And over on the right-hand side, we have a group of members of the BCS in a meeting, and they're connected to network 19. And how does the BGP table get updated and define what to do? So what actually happens is network 11, that's the IP address for YouTube. It actually says it takes YouTube IP address. I've substituted that for YT, but that means that the IP address for YouTube. And it prefixes its own number, and it says but basically what it's saying there is I'm network 11 and I've got YouTube. Does that make sense to everybody? And then network 11 broadcasts that to the adjacent networks. So network 21 gets that table and it goes, okay, I know that network 11 has YouTube, so I'll prefix myself to that. And I'm saying I'm network 21, I connect to network 11, which in turn will take you to YouTube. And network 11 also broadcasts that to network 66. Network 66 does exactly the same, prefixes its network ID, and it's now showing a path to get from network 66 to YouTube at 66, network 11, and then you'll find YouTube. And in turn, 21 advertises to network 13. Network 66 advertises to network 13. And you can see how the updates then cascade through the network. And by the time you get to the BCS team member sitting there in London, they actually have 3 routes to get to YouTube. All are valid. Now, again, a slight simplification, but fundamentally what BGP does is it will take the shortest route. So what it will do is it will take the top one. So it will say 19 to 33, 33 to 66, 66 to 11, and that will take you to YouTube. And that is the route map that BGP creates dynamically on an ongoing basis to define where you can find IP addresses around the internet. Does that, anybody get any questions they want to shout out? No? Are we good, David?
Yeah, if you do have any questions, then you can type them in the chat and then we will
I
pick
can't
up on
see in
them.
the chat, so you just need to shout out if there is anything comes up, please.
Yeah, sure, we will.
So-
Actually, it just came up. Martin Gee asks, and all in 512 megabytes.
Sorry, can you repeat that question, Diana?
So all the routing and everything it does, it's in the 512 megabytes.
Yes, it's in 512 megabytes. I always emphasize it's megabytes, not megabits. Yeah, the BGP table is quite large. Now, one of the things you should know is you can configure BGP manually. So the network operators could sit there and do this manually. The problem is it's slow, and configuration errors, and we'll come on to that later, can cause problems. So what tends to happen is they trust one another. So all these networks, 11, 66, 33, 19, etc., all of them, they all know one another. They trust one another. Yeah.
We have just one more question. Michael is asking, why wouldn't YouTube 11 broadcast directly to BCS? So why won't YouTube broadcast directly to 19?
He broadcast, YouTube doesn't do the broadcast, network 11 does the broadcast. What you do is you simply broadcast to the networks that you connect to, and they pass it along. You may not know that 19 exists. So in effect, it's a sort of cascade through the network as all the networks. 11 knows about network 66 and it knows about network 21. It broadcasts to them. They're connected to 13 and 33, so they broadcast to them. And in that way, it cascades through the whole network, as opposed to 11 having to have a complete map of the network that it then tries to broadcast to.
Yeah, thank you.
Now, one of the things is, and when I did my research on this, there was a very interesting comment. One of the senior researchers said the problem with BGP is it relies on the honor system. So basically, you accept what the other networks tell you. Your BGP tables update automatically as you receive updates because you trust one another. Well, BGP hijacking is a problem. Let's say network 66 is either it's a Russian network, for example, or it's hijacked by a hacker, Russian hackers or hackers from another country, and they get hold of it. And what they do is they actually say, actually, we own YouTube. Network 66 has the YouTube IP address, and they update their BGP table. So they're now saying, I'm network 66, you can find YouTube here. Nothing to stop them actually doing that. And then what they do is they then start to broadcast out BGP updates. Network 13 accepts it because it's working on the honor system. Network 33, it accepts it, it's working on the honor system. And those changes propagate through the internet. And what you end up with is a completely different table for the BCS team sitting in London on network 19. Now they say, right, we're going to send traffic to YouTube, and the shortest table, the shortest route is 19 to 33 to 36. So the traffic that they thought they were sending to YouTube is now actually going to a server sitting on network 66.
We have two more questions here. Sorry, Simon, for
go ahead.
interrupting. Dan is asking, is a copy of the BGP table stored in a cache similar to the DNS?
I mean, I think the question that you're probably asking, is there a copy that you can then compare to? And there have been attempts to try and validate the changes that come along against previous versions. But the trouble is it takes processing overhead. Because the BGP tables are being updated on a regular basis, they tend not to do that. I don't know if each network is storing a cache copy. They may well have, but they're not necessarily doing a check against the previous version. Because what that would do is it would actually impose quite a large, if the table's large, you then have to go through, validate all the changes, make sure that they make sense, and then distribute them. And that would actually slow down network changes on the internet. That tends not to be how it happens. As I say, there are initiatives around doing like digital signatures, etc., around it, but they're not, as far as I'm aware, fully implemented at the moment.
Another question is, what's the frequency for the BGP updates?
I knew somebody was going to. It's I can't remember off the top of my head, but it is fairly regular. They are coming out. Especially if you're a large network and something changes, you'll immediately announce it.
And another question is, in this case with the hacker, what would network 13 broadcast?
It depends if network 66. Well, what's happened here is network 13 broadcast. I'm network 13. I will take you to network 66 where you will find YouTube, or I can send you to network 21 11 in YouTube. So it's actually got two conflicting routes, but unless it actually physically goes in and looks at that, it wouldn't necessarily identify that. And what it would do is it would route according to the shortest route. So if network 13 hadn't picked up that malicious change, it would broadcast itself in the path through network 66 to YouTube and would send traffic to the fake YouTube address. Now, this has happened. I was going to explain this a bit later, but I'll explain it now because I think it's relevant. About quite a number of years ago, I think it was about 10, 12 years ago, Pakistan Telecom was actually asked, because they were the national carrier in Pakistan, they were actually asked to block a YouTube video which was considered blasphemous. So what they did was they did exactly that. If you replace that Russian flag with Pakistani flag, but they didn't mean to broadcast the upnet. What they did upstream, they broadcast downstream into Pakistan to all the local ISPs and networks that they owned the IP address for this specific video. And what would mean is if somebody inside Pakistan tried to access this video that was considered blasphemous, they would be taken instead to a Pakistan Telecom server room where they would get on a server and it would say, you have tried to access prohibited content. The problem came about that Pakistan Telecom accidentally broadcast upstream in the same way that I've shown you here that network 66 broadcast the 13 and 33. Pakistan Telecom broadcast to a network called PCCW. PCCW, working on the honor system, had no reason to doubt Pakistan Telecom's BGP update. They broadcast it globally. At least half of the global internet disconnected from YouTube as a result because they couldn't identify the correct path. So not unlike network 13 here or network 84, they had different paths to YouTube, couldn't resolve it, took the shortest path. It caused chaos for about 12 hours.
So in this case, conflicting routes are
yes.
regarded as alternative routes rather than...
Yes, that's right. And what happens is BGP defaults to the shortest route. It's actually part of the algorithm. It just says, what's the shortest route? That's the route we take. And the only way they actually resolved the Pakistan Telecom outage was they resolved it by disconnecting Pakistan Telecom from the world internet. Let all the BGP tables update correctly, made sure Pakistan Telecom had updated its BGP tables properly, and then they reconnected them onto the internet. So it was no small incident. Now, there's been more recent incidents where China and Russia have, quote, accidentally published a route that was invalid, and large amounts of data have suddenly flowed into Beijing or to Moscow, into one of the Chinese or Russian networks. When China did it, there was a huge amount of US military data suddenly went flowing off into China because that was the route that they thought was valid. Lasted about 10 minutes. China suddenly said, I'm sorry, we've made a routing mistake, and updated correctly, and the tables went back to being correct. Depending on whom you ask, it was either a legitimate mistake or it was a trial run for a potential BGP attack. There's not a consensus on which it was. I think some people think China was actually preparing to see if it would work as an attack. Russia's done the same. Some people say, no, it was just an honest configuration error. It depends who you ask. But it can cause absolute havoc on the internet. Now,
we have another question about this as well, whilst they're on the subject. So Ian was asking, what does one of these networks consist of? For example, a range of IP addresses, things that are in particular geography, and who typically administers a network?
Network 11, for example, could be AT&T. So it's a massive network. And they might actually have more than one AS number. BT is another network. It has an AS number. Google has an AS number. They have millions, literally millions of IP addresses, the large networks. Virgin will have an AS number. T-Mobile, NTT in Japan, KDDI in Japan, China Telecom. I can never quite get the Russian network name, Rostelcom or something. They're a global network. They have an AS number. So every network, but some of them can be quite small as well. Some networks can actually be very, very small. So it's everything from network carriers that you and I would recognize, BT, AT&T, etc., to fairly small ISPs. They're all ASs, autonomous systems, and they publish routing that they see based on their network interconnections. They don't have to worry about the whole network. They only have to worry about the people they connect to. So let me, just in the interest of time, I then wanted to just, I think all of us know how a botnet works, but I will just go through this very quickly. This was research we did into the Mirai botnet. A botnet is a robotic network. If any of you are familiar with the search for extraterrestrial intelligence, SETI, they did a program called SETI at home. You could download software onto your computer, and at night, if you left your computer on, NASA would then send, or SETI would send information to your computer and get you to do processing for them. And in this way, they could utilize hundreds of thousands of computers around the world to help with their processing power needs for analyzing radio data that they were doing as part of the SETI program. But botnets in the cyber world tend to refer to malicious malware, which has basically got onto your computer and press gangs your computer into acting in the interests of a bot master. So the bot master has some command and control servers, which we can see here, and they communicate with the command and control servers using the onion router, the Tor network. And they'll scan the internet for, in this case, the Mirai botnet scan for Internet of Things devices, which had the default password on the IoT device had never been reset. So a lot of things like CCTV cameras and stuff like that, they have a default password like password 123, and you're meant to reconfigure it when you install it. People didn't. So there was many of these devices out there. It gets the IP address of a vulnerable device, which is then sent over to the loaders. The loaders are then able, because they've got the default password and IP address, they can log into the Internet of Thing device, and they download the Mirai botnet. So at this point, the device has been press ganged into becoming part of the botnet. And they then run Mirai. They can download the Mirai malware and run it. Now, at that point, the targets are conscripted into the Mirai botnet, and each one of them then communicates. They continually communicate with the command and control center, which is constantly changing its IP address and updating that within the botnet. And then it will ask them to maybe send access requests, maybe TCP or UDP flood requests to the victim, which will then drop out of service. That's how botnets work. And the point I wanted to make about botnets is botnets are in effect a cyber rocket launcher. You can configure them to different payloads. Botnets have been used for DDoS attacks. They've also been used for distributing fake news on groups like Facebook and stuff like that, false information. They've been used for driving advertising clicks to generate revenue for people who are paying for advertising clicks. So botnets can be used for a lot of different uses. And what I wanted to investigate was, could you use a botnet to help facilitate a BGP hijack? So, right, what I'm now going to do is drop out of this, and what we've got here is a model of the network, the internet, and I'm going to show you a very simple model. That's a very simple model. The red dots are what are called tier 1 ISPs. Now, these are the very biggest networks in the world. Believe it or not, I don't think BT is actually a tier 1 ISP. I'd be happy if anybody corrected me on the call, but when I seem to remember at the time when I did my research, BT was a tier 2 ISP, which means they buy transit from other networks. Tier 1s don't buy transit. They tend to span the globe, or very large parts of it, or very large geographies. PCCW would be a very good example of a tier 1 network. Tier 2s, they buy transit from the tier 1 to connect their geographies to the rest of the world, and then they sell transit to much smaller networks, which I've shown as the green or the blue networks. Now, what I wanted to demonstrate for you was, imagine that network 217 there decides to advertise a fake IP address, and it wants to advertise all the IP addresses on network 318, which is somewhere else in the network. So what we'll do is we'll do a fake route advertisement, and we'll advertise 318, and we'll advertise it on 217. And there it is. And I've prefixed it with a 6 just to show that it's a fake ID. So 217 is actually advertising a fake ID for network 318 and all the IP addresses there. For simplicity, the level 3 or the level 4 networks here, the green and the blues are the same. I've assumed that the number is the same as an IP address just for simplicity. So 217 is actually saying I've got network 318 attached to me, which is false. And to actually show the impact of that, I'm using an algorithm which does shortest path analysis, and all the nodes that have gone purple, they think that 6318 is the valid network 318 because it's the shortest route for them. Their BGP table would update, and their shortest route would take them to 6318, which is a false network. Does that make sense? Does anybody have any questions about that?
No questions about it so far.
Okay. So that illustrates the impact of it. So I'm actually going to now show you on a slightly larger scale, because I basically built a larger model. This is a larger model. You've got a left side of the network, so you can imagine that's, you know, America, Europe, and then, you know, the right-hand side would be Eastern Europe, Asia, maybe Russia, Asia, China, etc. Asia Pacific. So global network, big tier 1 carriers at the center, which are the ones 111, 112, 113, and 114. They're the tier 1 carriers. We've got a number of tier 2 carriers like BT, etc. People like that. They're colored orange, so they're prefixed with a 2. And then you've got all the smaller networks, which are the 3s, which are the much smaller regional local geography network. So what I wanted to show was, imagine somebody gets in and inside network 228, which is down in the bottom left-hand corner. What they actually managed to do is they actually managed to advertise a false address for one of the networks that's actually attached to 228. So input node to advertise is let's just say 300. And then we'll say 228. Brought. And hopefully you can all see a false network 300 or address 300 has now been advertised by 228. So 228 is actually advertising 2 networks. One is 300 and one is 6300, which is pretending to be 300 but is actually false. Now, if I actually say, if I ask it to show me and color the impact, you'll see there's no impact. And the reason is because they're both sitting on the same tier 2 network, the shortest route hasn't changed. And as I said, BGP takes the shortest route, and the assumption I made when I modeled this was if the route to the valid network and the route to the false network are the same, traffic will default to the valid network. But then imagine that a BGP, a botnet, manages to infect other networks around my internet model here. I think it's and what you can see is you'll see a number of networks have been colored pink. And the pink networks, there's 5 of them, 213, 332, 339, 224, have all gone pink because they have been affected by botnet. And they've advertised the route, which I've shown, directly to 6300. So they're advertising a false route. And the purple illustrates the scale of devastation on the internet. So large parts of the internet are now, their traffic will default to the false address, not the valid address. And that's with a fairly small attack. I said, I think I put in 5, 4 or 5, which is a very, very small number. There's a total of 100 networks there. 4 of them have got infected with a botnet, and basically the devastation is very, very large. A very large part of the internet is affected. Yeah, the last attack that I will show you. We'll clean things up. We'll do another smaller one. We'll publish a false root. We'll publish. You'll see it in a second. So network 224 is falsely publishing the network 381 by prefacing it with a 6. The impact of that is actually very, very small. You can see only a small number of networks have actually gone purple, so they're affected. So everybody in 224 is affected. Their traffic will go to the false route. The rest of the internet isn't. But what I would say is, if you added a route, and what I've done, I'll show you in a second. I've added a route from 111 to 6381. Now 111 is a tier 1 network, so we're assuming it's been affected by a botnet, and it's now advertising 6381. And we will have a look at the impact of that. And you see a massive amount of the internet suddenly goes purple because, in fact, the complete western side of the internet has gone, is now being directed to the false network, because a tier 1 network is so central to network infrastructure that it just has a massive impact if it gets infected. Now, when I did my research, one of the things I was worried about was I wouldn't be able to find much evidence that routers can be hacked. It turns out they can. They're no more secure than any other device. You could actually argue they're even less secure, because often they're not necessarily updated as much as other equipment. So some sort of hack into a router, either with a botnet or some other way, and then publishing false routes to a false BGP could have devastating consequences, which hopefully I've illustrated with the model. Are there any questions at that point?
You definitely have demonstrated that. There is a question related to the last model.
Yeah.
In which, how is 113 not being corrupted here?
Believe it or not, because 113 has a direct connection to 225. If you can see, if I can show it here, 113 is connected direct to 225, so its path to 381 is 2 jumps. Its path to 6381 is also 2 jumps, and the logic that I made was, if the path to the corrupted address and the valid address are the same, I assumed that the valid address prevailed. So in effect, what I said was the corrupted address had to be more attractive. It had to create a shorter path. So that's why 113 isn't infected here. It's actually, the path is the same to both the valid and the invalid addresses. Does that make sense?
Yes, it does. And there are a few other questions, but therefore at the end of the lecture.
And anybody that's interested, I just use Dijkstra's algorithm. It's it's part of the Python library. You could just pull up Dijkstra's algorithm and use that. That's how I did the calculation. So does it happen? Yes, I've already told you about YouTube. I've told you about some of the other cases where this does happen. Other shenanigans with BGP routing are also quite interesting, and I'll just run through these very quickly because I noticed we're coming up on time. China Telecom has a number of POPs in North America, or it did, and it used to advertise a route to South Korea from its North American POPs. And I think the Canadian government was actually using China Telecom route to get to South Korea. So it was assuming, okay, I'm giving my traffic to China Telecom in Canada, and it's routing my traffic over to South Korea. What was actually happening was, as I mentioned at the beginning, BGP, external BGP, says nothing about how you route your traffic internally. So China Telecom was advertising South Korea. What it was actually doing was shipping the traffic first through China, almost certainly making copies of all the traffic, and then shipping it on South Korea. And the way that I would describe that is, it's a bit like if you get on a flight in somewhere in Canada, and I say I'm flying you to South Korea, you jump on the flight, and I fly you into Beijing. And I open up your bags and I check everything, make a content of your laptop, copy of your laptop, put it all back in your bags, and then put you on a connecting flight to South Korea. This has actually caused enough consternation. I think some of the POPs have actually been shut down, and there's been a lot more focus on actually what internal routing happens by network providers. And I know that some networks are now refusing to connect with one another depending on geopolitical tensions, because they're worried about how traffic is moved around the world. So I don't know if you can see that. It basically says data transits through internally, pops in the mainland, and is then transmitted over to South Korea. It's not what you thought was going to happen. So the sort of punchline is, what really should keep us awake at night? What I would say, we have gone from this, the idea of the lone hacker, the lone wolf persona, hacks for fun and interest. They hack to prove their skills. They're interested in the hack. They weren't usually driven to cause damage. If they did, they used to deface a website. And really, in less than 15 years, we've gone to nation state hacking groups, dedicated government units, politically aligned hacking groups, world-class technical skills, and legions of them. North Korea seems to hack mainly for financial incentives. China, a lot of stealing of intellectual property. And I think it's fair to say we are almost certainly in a cyber war with Russia at the moment, and possibly to a lesser degree Iran. What can we do about it? Well, the truth is, you actually can't do a lot about BGP hijacking. You can try and look at all the route changes, but it slows things down, and configure. Some route mistakes have been put down to misconfiguration. BGP hacking still happens to this day. I read about a crypto attack recently where they redirected cryptocurrency transactions using BGP hijacking, and then mimicked the necessary handshakes and stole money. The problem is, as I said at the beginning, the internet was not designed to be secure. So what can we do about it? One is, I think we all need to think about disaster recovery and business continuity, assuming a disrupted internet. I mean, I wrote an article on this. If anybody's interested, it's on my LinkedIn profile. We have sleptwalked into a situation which a vast amount of our critical infrastructure is sitting on the internet. Everything from buying your morning coffee at Pret to banking. If you've moved into the cloud as an organization, everything's on the internet. You probably, I think most organizations would benefit from thinking what a minimum viable proposition would look like in the event of internet disruption. I don't think many companies do, but if you couldn't get on, log in the morning, what would you do? How would you work? And one of the things that I don't think has been investigated anywhere near enough is disaster communication between organizations and between countries. So, for example, if the SWIFT network was hacked, or one of the major banks, and they went down, suddenly you're trying to do cyber forensics, disaster recovery, all within cyberspace between countries, maybe multiple countries, different jurisdictions, different languages. It's not just a single organization that's being hacked. It has a cascade effect across multiple geographies and organizational structures. And I don't think that has really been thought through well enough. The NCSC in the last month has issued several warnings. It's actually described China as an existential threat to the UK in cyberspace. The same with the Wagner Group in Russia. And most recently said they are very, very concerned about the increasing number of hackers who are able to go online onto the dark web, darknet, and basically pick up cyber tools that for hire, for rent, and apply them wherever they want. One quote I had from a security expert in the US was, he said it was like giving rocket launchers to teenagers. They can just basically go on. There's middlemen that will provide you access to the networks. You buy the tools, you lease the tools, etc. All of this is going on in real time. And my concern is I really don't see the world, the business world, the political world, being anywhere near savvy enough about what is going on in this sphere. So that is the end of my material. That's me at my desk.
Thank you very much, Simon, for all of that information and for the concluding remarks. There are a few questions if you feel like we have time for them.
Yeah, you can. I think if you do a search, you can find the BGP tables. I don't think they're secret in any way. That's one last question I saw. Could a blockchain model be used to maintain? That's actually a very good question. I think there has been, there's something called manners, and I didn't go into manners a lot when I did the research. It is a way of using some, not necessarily blockchain, but it was like using digital signatures, which, you know, part of the foundation of it, to try and validate them. I think one of the concerns was because of the rate at which BGP updates are put out, if you then start doing some sort of either blockchain model or checking digital signatures and then re-encoding stuff, it puts an overhead, processing overhead on the routers, and the BGP updates are sufficient in volume that actually starts to slow things down, and the dynamic nature of the internet to be able to respond to network changes is affected.
Diana?
Yeah, I think most of the questions have been answered, so
What sort of, I just saw one there, what sort of resilience does tier 1 ISPs have to avoid such attacks? Well, one is they only, in fairness, they only connect with other very, very trusted networks. So if you're running a small ISP, you trust me, you're not connected to a tier 1. The reason that the Pakistan Telecom network was such a devastating attack was Pakistan Telecom, being a national carrier, had a valid reason to be connected to PCCW, and it was an accident. It was an invalid route declaration. So I think unless a tier 1 ISP was hacked and somebody got in and changed it, I think it's unlikely they're going to get caught out. But I think one of the problems is what's beginning to be recognized is that not all network providers, depending on their geopolitical alignment, are safe anymore. And what I think we could see in time is the internet fragmenting and certain blocks, geopolitical blocks appearing for the internet, where and the routing changing between them. You know, they don't interconnect in the same way.
Thank you for all of the information and that you answered the questions. I think that's all for now. Everyone's thinking. So
I hope
it was a great presentation, really.
Thank you very much for your attention. I appreciate it. Enjoyed giving it. Thank you.